So for today's class, we're going to be continuing with chemical equilibrium, but we're going to be looking at interpreting our graphs for dynamic equilibrium systems. So for our diagrams, we're going to be looking at the reaction rate versus the time. We're going to be looking at the amount, implying the number of moles, the mass, the volume, versus, again, the time. And we're going to be looking at the concentration versus the time, and looking at how all of this is affected whenever we make a change in our system. For each of these graphs, the time is going to be the independent variable and will therefore be placed on the horizontal axis, or what we know as the x-axis. And either the concentration, the amount, the rate of the reaction, in this case, would be on our y-axis because it is dependent on the time. Now, to fully understand this concept, we're going to be using an example, and we're going to be changing things in this example, and seeing how the graph reacts, or how the graph is going to change when the system reacts to the change that we have introduced. So for the reaction that we are going to be looking at today is the sulfur dioxide reacting with oxygen to produce sulfur trioxide. Now, for the next coming graphs, these are the keys that we need to remember. We need to remember that the dark for the rate of reaction, the dark line is our forward reaction. The reverse line is going to be dotted line. For the concentration of oxygen would be shown with a solid dark line. The concentration of sulfur dioxide is going to be shown with dots, equally sized dots, whereas the sulfur trioxide will have length and dot, length, dot, and length and dot. First, we need to just look at our reactions. And just make an analysis of our reaction. We'll start with looking at the number of moles on the left-hand side compared to the moles on the right-hand side. So on the left-hand side, we have 2 sulfur dioxide reacting with 1 mole of oxygen to produce then 2 moles. So for the 2, we have 3 moles being reproduced on the 2, 3 moles being produced on the 2. On the left, we have 3 moles being reproduced on the left, and we have 2 moles being produced on the right. Just give me a second. Okay, so we want to make an analysis of our equation over here. So let's start with comparing the number of moles that are made on the left-hand side and the number of moles that are made on the right-hand side. The number of moles that are made on the left-hand side is going to be the 2 moles from the sulfur dioxide, the 1 mole from oxygen, giving us 3 moles from the left-hand side. And the right-hand side, we only have that 2. Now, here our change in enthalpy is negative, implying that the forward reaction is exothermic. Therefore, the reverse reaction would be endothermic. This is a homogeneous reaction, so all of the reactions are all solids. Okay. So when the reaction starts, let's look at how those 2 graphs are going to look like. If we remember from theory, we know that the rate of reaction is directly proportional to the concentration. So it means if we have a higher concentration, we would have a high rate of reaction. Now, if we look at the concentration, this is then the concentration of our sulfur dioxide. That is the concentration of our oxygen. And this there is the concentration of our sulfur trioxide. Now, for the forward reaction, we have a high concentration of both the reactants. So therefore, we will start with a high rate of reaction. And over time, the reactants are going to be used, decreasing the concentration of your sulfur dioxide and your oxygen. Thus, you will see also a decrease in the rate of reaction. Now, for your forward reaction, when you start, you do not have your product. You don't have the reactants, right? That are for your reverse reaction. So your reverse reaction and the concentration of your sulfur trioxide is going to then start at 0. Once the reaction picks up and we produce sulfur trioxide, that sulfur trioxide will start to then produce oxygen. So the rate of the reverse reaction is going to steadily increase as the concentration of sulfur trioxide increases. Now, this is going to increase. The rate of reaction is going to increase for the reverse reaction, and the rate of reaction is decreasing for the forward reaction. So over time, we will get that the over time, we will see that the rate of the reaction for the forward will decrease so much that it meets the rate of the reaction for the reverse as it increases with time to a point where they are equal to one another, and we call this position equilibrium. You can tell from the rate of the reaction that the reaction is still taking place, but the rate at which we are making the products is the rate at which we are using them. Now, for your concentration or for your number of moles, you would see that once your system reaches equilibrium, then the value is going to remain the same. So the concentration or the number of moles is going to remain the same. And at this point, we will say that our system has reached equilibrium. So let's go ahead and add some changes and see how our system is going to react. The first change we're going to make is that we are going to add more oxygen. So let's see how more oxygen is going to make the system behave. If we look first at the concentration side, there is oxygen. Remember from our previous graph, it had reached equilibrium, so the concentration or the number of moles was constant. Now, the number of moles and the concentration will go up because the concentration is the number of moles divided by the volume. So if we increase the number of moles, we also increase the volume. So we're expecting this behavior to happen because we have changed the number of moles, thus the concentration and the number of moles of your oxygen will increase. Now, according to Chatelier's principle, the system should react in a way that it favors the reaction that is going to then decrease the oxygen. Because the oxygen is being used in the forward reaction, you can see that your forward reaction takes a sharp incline, right? And then from there on, we have an increase in the rate of reaction. It will decrease with time. And as we make more sulfur trioxide, the forward reaction also increases until they reach their equilibrium position again. Okay, then we're going to change the system again. Let us say that we have now removed the sulfur trioxide. The sulfur trioxide is the SO3. Oh, this is the graph we're going to have when we have removed the sulfur trioxide. Now, removing the moles in terms of sulfur would also change the concentration, because the concentration, again, is definitely dependent on the moles. So we can see the sulfur trioxide taking a sharp dip, and we know that the rate of reaction is directly proportional to the concentration. So when our concentration decreases, then the rate of our reverse reaction would also take a deep decrease. Right. Now, according to Chatelier's principle, the system is trying to fight back by increasing the sulfur trioxide that we had. And it would do that by favoring then your forward reaction. So you can see there would be your forward reaction would start over again so that it can produce more sulfur trioxide. And as it produces more sulfur trioxide, we will see an increase in the rate of reaction for our reverse reaction. Let's not forget that in this case, sulfur dioxide, oxygen and sulfur dioxide is also going to be used, thus we see the decline in the number of moles and also in the concentration of those two. Let's go to the next change. Let us say that we are going to then increase the temperature of the forward, increase the temperature of the system, not being specific to say the forward or the reverse reaction, but increasing the system as a. Now, if we increase the temperature, we understand that first and foremost, the rate of reaction is directly proportional to the temperature. An increase in the temperature will increase the rate of reaction. Thus, you'll see here in the beginning, both your reverse and your forward reaction are going to be increased, because temperature increases the rate of reaction regardless of whether it is exothermic or endothermic. But the extent to which it increases that rate of reaction is dependent on whether it is endothermic or exothermic. We said previously that our reverse reaction is endothermic, so the reverse reaction is going to be favored. Why? Because it's going to oppose the change that we've just made. We have increased the temperature, and by favoring the endothermic reaction, we're going to oppose the changes that we have made, because the endothermic reaction is going to use that heat. So we can see that although both of them increased, the endothermic reaction increased more, and after that there was a slight decrease as time goes by, right? Because we're going to be using sulfur trioxide, so the concentration is going to decrease with time, and when the concentration decreases with time, the rate of reaction is going to decrease with time. Now, because we're favoring the reverse reaction, our reactants are now being made. We can see there's an increase in concentration of oxygen and sulfur dioxide. So because we're increasing the oxygen and sulfur dioxide, there will also be an increase. Now we can see, due to the change in concentration of our forward reaction. Let us now look at what is going to happen when we change the temperature, but this time we decrease the temperature instead of increasing the temperature. We have a graph that shows what's going to happen. So we know again that the rate of reaction is directly proportional to the temperature. So if the temperature decreases, the rate of reaction decreases. As you can see at the top there, both of them are going to decrease, right? But the extent of the decrease is dependent on whether it is exothermic or endothermic. So because the reverse reaction is endothermic and requires heat, it's going to decrease even more, right? Whereas the forward reaction would only decrease slightly. Now, because the rate of reaction has decreased, and in this case, we can see our reverse reaction is continuing on, it will produce more of our sulfur trioxide, causing the rate of reaction for our sulfur trioxide to increase until again this one decreases and then this one increases to a point where they meet. The next thing we're going to be looking at is now the change in moles, actually the change in volume, right? So what we need to understand in this case is the change in volume is going to affect your concentration. Okay, so let's look at that reaction and also let's look at the equation that gives us the relationship between concentration and volume. When we change pressure, we're going to normally change it by changing the volume, right? So in this case, we increase the temperature by decreasing the volume. If we look at the equation, C is equals to N over V, we will realize that C is inversely proportional to the volume, implying that when the volume decreases, our concentration should increase. Now, concentration, we calculate the concentration for all of our reactants and products. So we can see the concentration of oxygen went up, the concentration of sulfur dioxide went up, the concentration of sulfur trioxide went up, all of them went up, right? But we know according to Chatelier's principle, it's going to favor the side that releases the least amount of moles. Now, concentration went up, so then our forward reaction is going to be favored. Why? Because our forward reaction only produces 2 moles, whereas our reverse reaction produces 3 moles. So it's going to be favored, and we can see over time there will be a decrease in the rate of the reaction for the forward and an increase for the reverse as we continuously make more sulfur trioxide, and we see that the oxygen and the sulfur dioxide are going to decrease with a and they're going to decrease as the forward reaction was favored. It's the reactants are being used up. Okay. Now we saw the change in the concentration. We now need to look at what would be the change in the moles. Right. So by changing the volumes, we do not change the by changing the moles, we do not change the by changing the volume, we do not change the number of moles whatsoever. So you can see, unlike here in our concentration, we had an incline, right? Over here, the number of moles is not affected at all by a change in the volume. We will take a look now at decreasing the pressure by increasing the volume. So by decreasing if we wanted to then decrease the pressure, we would do this by increasing the volume. So we said that concentration is inversely proportional to the volume. So that means that if we increase the volume, we are then going to decrease the concentration, and we can see it in the concentration graph that all of my products and reactants are going to decrease with regards to concentration. Now, we understand that the rate of reaction is inversely proportional to the concentration. If the concentration comes down, the rate of reaction is going to go down, but it will go down for our forward reaction. Reason being is we are going to try to increase the pressure by favoring the side that produces the more moles. Now, for the forward reaction produces 3 moles, whereas, the forward reaction produces 2 moles, whereas the reverse reaction produces 3 moles. So because there's more moles being formed, when you go in reverse, you can see that it was favored. So it didn't go down whatsoever, and our forward reaction was not favored, so it decreased a lot. From there on, we are going to go ahead and produce more of our reactants and decrease the concentration of our product. With a decrease in concentration of our product, right? So here we can see our reactants are increasing, products decreasing. With an increase in concentration, we can see also that the forward reaction is now going to be favored. Again, the change in volume makes no change to the number of moles. The change comes after it is now reacting to the change in the equilibrium position. Then we have a change by a catalyst. So if you can remember from our Monday class, we said that catalyst's job is to increase the rate of reaction without being involved in the reaction itself. Now, when it comes to catalyst, most of the time it's not specific. It's going to be there to increase the rate of reaction, and it's going to increase both the reverse and the forward reaction at the same rate. So there's going to be no change either in our concentration or in the number of moles. Any questions, you can go ahead and send them to me.